In this video, I'm going to talk about how current and voltage behave in circuits. Before we begin, here's just a key of different circuit elements. The ones you're going to see in here are power source and resistors. Just for reference, there's a switch and a light bulb shown as well. So the first thing I want to talk about, again, my focus is on current and voltage. So when we talk about current in the circuit, it's important to note that current cannot be created, it cannot be destroyed. So whenever current leaves the battery in this particular circuit, it has no place to go other than through our single resistor and then complete its path and return to the battery. So whatever the current is through the battery, let's just say for sake of argument, it's 8 amps. That means I have 8 amps that run through this resistor. Now voltage on the other hand behaves a little bit differently. If I want to think about the voltage, what's going to happen, I should be considering the battery effectively like an elevator. And so here's an elevator shaft, and what the battery does is it brings something up to a high voltage. Perhaps this is a 9-volt battery, so it brings up to 9 volts. Now what resistors are like ladders where you step the voltage down. So as the current travels through the resistor, is going to drop 9 volts and come back down to the ground. Now, when I use this analogy, I'm basically setting voltage equivalent to height to show you what would be happening in the voltage in the circuit. Everywhere along this line would be 9 volts, and then everything along this line here would be 0 volts. So the battery takes us from 0 volts to 9 volts. That's why it's a 9-volt battery. That's how we define a 9-volt battery. Taking us from 0 volts to 9 volts. And the resistor consumes all 9 volts, bringing us back down to 0. Now, if we get into something a little bit more complex, like a series circuit, this is a series circuit, and it's defined as series because, well, these 3 resistors, 1, 2, and 3, are all in series with each other. Just like in the previous circuit, whatever current runs through this particular battery has to pass through R1, R2, and R3. There's no other alternative path. So the current, which is abbreviated with the letter I, the current is the same everywhere. Current can't be created or destroyed, so it is not consumed by resistors. It is not created by batteries. Now, the voltage, using our height analogy again, here's the elevator shaft, and the voltage is going to bring us up to the maximum voltage. And then what we're going to have is 3 ladders, 1, 2, and 3. Now our ladders don't necessarily need to be equal in height. It'll be based on what the resistances of these 3 things are. But in our model, the battery raises the voltage up, giving it electrical height, if you will. And the first resistor takes some of that height away. The second one takes some more away. The third one takes the rest of it away, bringing us to 0. Now, without knowing more specifics about what the resistances are, I can't necessarily say what the voltages would be in between them. But for sake of an argument, let's assume that this is a 12-volt power source. That means this line would be sitting at 12 volts. And the one thing I can say for sure is that this final return line is sitting at 0 volts. Again, the 12-volt battery is defined by taking a 0-volt line and raising it up to 12 volts. Perhaps we have a very big resistor at first, and this very large resistor. Perhaps the resistor consumes a total of 8 volts. So that would mean that after resistor 1, our line's down to 4 volts. And perhaps our next resistor doesn't consume that much. Perhaps it only consumes 1 volt. So our next resistor would bring the total voltage from 4 down to 3 volts. And then our last resistor would, of course, consume the remaining 3 volts. The current through this entire circuit will remain the same everywhere. Now, how did I get this 8, 1, and 3? I just made it up, just as an example. We'll get into more detail in a future lesson as to how much voltage each resistor would actually consume. If we go into a parallel circuit, what the parallel circuit does is it creates options. So in a parallel circuit, there's more than one path. So using my height analogy, here's the elevator shaft. Once again, the elevator raises us up. But what we have is we have three different ladders. 1, 2, 3. So three different ladders can take us from the highest level down to the lowest level. Now, this is going to cause the current to behave much differently than the previous circuits. The voltage will also behave differently in the previous circuits. This is where a lot of people get confused. They think that the voltage should split, but that's not true at all. Let's assume this is a 9-volt battery. Again, just made that up for the sake of an argument. Everywhere along this line is 9 volts. Voltage is established across the entire power line. And everywhere on this line is 0 volts. Again, that's defined by the battery. The battery's job is to take 0 volts and raise it up to 9. And each one of these resistors would consume 9 volts. Now people think, well, that's a consumption of 27 volts. How's that possible? And that's because of a misconception of what voltage is. Voltage is not energy. So it's perfectly fine to have 1, 2, 3 different paths that take you from 9 volts down to 0 volts. What will change, though, is the current. If my analogy, I go ahead and say, we talk about people. So perhaps I have 6 people here, okay? And there are 3 ladders to choose from. Now, if these ladders are all equal, it makes sense 2 would go down 1, 2 would go down 2, and 2 would go down 3. But perhaps they're not. Perhaps ladder 1 is very wide and ladder 2 is very skinny. So maybe 1, 2, 3 people go down here, 1 person goes down here, and then the other 2 people go down the last ladder. That's possible too. And in a future lesson, we'll talk about how we will be able to distinguish it. Regardless, though, all the ladders are taking us from 9 volts down to 0 volts, or from 9 to 0. Now you may think, well, I thought electricity will favor the path of least resistance. That is true. Now the key word there is it will favor the path of least resistance. We did not say it would ignore all other paths. It's kind of like if there's 3 different ways to get from point A to point B through traffic. Now, if every single car took the route that has the most lanes in it, well, that means the other 2 routes are effectively useless. The other 2 routes may not be as good as the, say, 4-lane road, but that doesn't mean that it's always worth taking the 4-lane road and ignoring the other 2 routes. Because if everyone chooses the same path, you're going to end up causing your traffic to get gridlocked. But if some people choose some of the not so pleasant routes, well, there'll be less traffic there, so it may actually be a better choice. And electricity does the same thing. Certainly, of these 3 routes, 1, 2, or 3, more current is going to favor less resistance, but that doesn't mean current will completely ignore the higher resistance values. Now, the last one we'll look at is what if we get into a complex circuit like this? This is a series and parallel circuit combined. So in this particular one, I'll use a 9-volt battery once again. And we'll say, well, that means this line right here has to be sitting at 9 volts. And our return line has to be at 0 volts. Again, because the battery took us from 0 volts to 9 volts. That's how we know that. I'm making up this number. Let's just assume that this resistor consumes 6 volts. That means this line sits at 3 volts. 9 volts came into the resistor took away 6, 3 volts were left. So that also means that these remaining resistors would consume 3 volts. As for current, let's say for the sake of argument, coming out of my battery is 6 amps of current. Those 6 amps have no choice but to go through the first resistor, R1. But then they're going to split here. Perhaps this is a least resistance path, so maybe 4 amps choose this one and 2 amps choose this one. Now, when the 2 amps come through this resistor, they're going to rejoin with the 4 amps that went through this resistor, and we're going to go right back to 6. Because again, we can't create or destroy the current. Using our analogy about height, here's the ground level, here's our elevator. The elevator takes us all the way up to 9. And in my current analogy, I use 6. So let me draw 6 stick figures. 1, 2, 3, 4, 5, and of course number 6. Now, looking at this circuit, I have no choice but to go through R1. So I'm going to put one ladder. There's only one way to get from 9 down to 3. But once I've done that, there's actually 2 options. I can go down ladder number 2, or I can go down ladder number 3. So that's how our analogy would work for this. All 6 of these people have to go down ladder number 1. Now, perhaps 4 of them choose to come down this ladder, and 2 of them choose to come down this ladder, and eventually all 6 people will meet back here.